Welcome back. Now we are getting into some of the very important properties that are very specific to molecular dynamic simulation. As you know, there are other methods which we will talk a little bit later in this course called Monte Carlo simulation, and that is where we can do statistical understanding or what we call stochastic modeling of the molecular dynamic system, and we can look at the statistical averages, but in terms of snapshots, or when we do enough statistics then we look at the properties. And that is where what happens, because we are looking at one statistical state space to another one, we are losing the understanding of what we call as dynamic properties. So, dynamic property is a particularly important thing for molecular dynamics, because it gives you understanding of the dynamics. And so, although Monte Carlo can be used to calculate pressure, calculate other properties thermodynamically, but if you want to calculate some of the dynamic properties like mean square displacement, velocity autocorrelation function, or even some of the transport coefficient like if you want to calculate thermal conductivity, that is where the molecular dynamics is particularly applicable, and that is where you would use that. So, let us start now going into the mean square displacement. Now, the idea of mean square displacement is very simple, that if you look at a particle at time t0, and then and you know its x, y, z coordinates, and then you go to time t delta t or t1, t2, t3 in the series of time steps, then you look at its position, and if you find the distance from the original position, then you know how far it has gone from the original position, and that is called displacement of the particle. So, if you look at the displacements over number of time step, and you create the square root of that mean square displacement, then you know that, or the square of those displacement, primarily because you are looking not in this case the direction, but you are looking at the amplitude of displacement. So, you create the square quantity, so it does not matter positive or negative, you want to find out the displacement. So, you are now looking at the mean square displacement, and mean because we are doing average of this mean square displacement on all n number of such time steps. So, with this understanding, now we are really ready to look at mean square displacement on your slide. So, delta r square, which is the mean square displacement, is equal to 1 over n number of particles, I position atom at time t and the position at time t0. So, now we are looking at the displacement over certain number of time steps, and then we are averaging that over n number of particles, and also then later on we create time average as well. So, if you look at, but in this case, because the dynamic property, you want to look at the change with the time. So, you will focus on the average which is done over number of particles, but do not average on specific time stage, because then you will smear that whole effect, because you want to see the changes in the mean square displacement over a certain number of time steps. So, you can average over those number of time steps, but then you do not average, go again another time step, and then you look at the increase or decrease or being constant in this particular mean square displacement. So, if average over all particles mean square displacement that particles have moved during the time t. Mean square displacement is 0 at time t0, which is the initial position, and grows t square with a coefficient proportional to kb t over m. If you look at this, kb t over m is the kinetic energy part, which we understand from specific heat as well. In the solid, you know that the mean square displacement will grow to a characteristic value, but then it will become constant, because the system is holding the crystalline structure and moving around this crystalline space. So, there is some distribution of trajectory around it, which we have seen earlier in the molecular VMDL. So, you could see those trajectory around the particles, but it is not growing with the time. So, it will go to a certain value and become constant with time. So, that will show that it is a dynamic, in dynamic sense it is a solid system, because it is adhering to certain number of the diffusion level. So, it cannot really grow with the time, but it will become constant. However, if you look at the liquid system, all atoms diffuse continuously through the material, as in Brownian motion. So, now you are looking at the displacement going random walk, which is the Brownian motion, and then with that you are able to see they are displacing, and as they are displacing, their displacement is increasing with time. So, there is a linear increase in the mean square displacement. That is clear indication that the material is in the liquid phase. So, this is in a way this is another order disorder parameter. However, it is not coming from the structural perspective, but it is coming from the perspective of dynamism of the particles. So, if you look at that, then we have this behavior that we can calculate for liquid argon. So, here is what you can see on your slide. Here is a square displacement versus time. So, if you look at a liquid phase, in this case diffusion constant, we can also calculate diffusion constant at the limit time t is equal to infinite, delta r square has become 2d, the distance, and the d diffusion constant. So, this is the slope of the curve. Slope of the curve is diffusion constant in this case. So, now you are looking at the diffusion constant, and that is where from mean square displacement we are now able to look at the diffusion constant for that particular system. This is a liquid. In case of crystalline, is essentially wobbling around the central position and 4.3, and that is where if you draw a line, you will see it is a sinusoidal behavior up and down, because the crystal is essentially like a spring, is wobbling with the spring energy inside, and that and the configurational of their structure. So, this is a crystalline structure and this is a liquid structure. So, again if you want to identify first order phase transition from crystal to liquid structure, you can also use mean square displacement. You can also use G of R, radial distribution function. In fact, you can also use the jump in the potential energy curve, which is very indicative of first order phase transition. So, going forward, now we look at that property calculation in MD using time averages. So, now we are looking at the time averages of the properties, which is very important factor, because now we can calculate what we call is average over time step of NT in a trajectory, which is a discrete changes in the property. Now, we are also going to be able to find correlation between two different properties, starting from A at time 0, B at time t. And so, now if you look at time correlation function, then we are able to find out how one property changes against the other and how are they correlated in terms of time variation. Or you can calculate its own variation with terms of time. So, if I take myself as a particle and see where I was at time t 0, and now if I calculate all my movement around that time and create what is called self correlation function. It is possible that I hang out in a particular place more often than the other, then my frequency of hanging out in that particular location based on the autocorrelation function can be found. So, now I can find the frequency of my arriving at particular location over and over and over again. So, that is the basic concept behind what we call as velocity autocorrelation function. Now, this is another very, very important parameter which will connect us from what we call the mechanical properties to dynamical properties to what we now call vibrational properties. As I said, in a particular material, let us take an example of liquid water, you have HOH. So, if you look at oxygen is connected with two hydrogen atom. So, H1 O H2, the another hydrogen atom there. So, if you look at, they have bonded and non-bonded part of the potential function. In the bonded part, now we are looking at the vibrational frequencies. So, now you will use what is called velocity autocorrelation function. So, if you look at this slide, so we look at the V0, average of V0 and Vt, and now we can do that discretely over n number of atoms, I is equal to 1 to n. The first what we say is the outer loop, and inner loop of summation is k is equal to 1 to n I. So, now we are looking at an atom I at time t k and at time t k plus t. So, this is where the velocity autocorrelation function gives information about atomic motion of particle in the system. Since it is correlation of particle velocity at one time with the velocity at the same particle another time, the information infers to how a particle moves in the system, such as diffusion. So, if you look at the velocity autocorrelation function, and if you look at that at time t0, that gives you what we call is diffusion coefficient. So, that is called Frankel-Smith diffusion coefficient d0, and that uses the Green-Kubo relationship, can provide links between correlation function and material transport coefficients such as thermal conductivity and diffusion. So, now we are getting into very interesting area with velocity autocorrelation in order to understand dynamical properties of material, which are the transport coefficient, as well as we are looking at other advanced properties of vibrational spectroscopic or vibrational frequencies, which we sometimes also call power spectra. So, we will pursue this further. We will stop here, and then we will look at some of the advanced dynamical properties of the material. Thank you.